Imagine a pop-up food stall that only exists for the exact second someone is ordering. There is no shop sitting empty paying rent all night. The instant a customer walks up, a fresh stall snaps into place, cooks the one order, hands it over, and then quietly folds away again. If 100 people show up at once, 100 identical stalls pop up side by side, one per customer, and vanish the moment each is done. You pay only for the seconds a stall was actually cooking, nothing for the quiet hours. That on-demand, appears only when needed way of running code is exactly what a serverless function does. Running a server day and night to handle bursty traffic is wasteful and high maintenance. You want code that simply runs when called and costs nothing when idle. But something still has to find hardware, isolate your code, and run it safely next to thousands of strangers. AWS Lambda is a function-as-a-service platform. You hand AWS a zip of code and a trigger. AWS stores the code, and only when an event arrives does it build an isolated execution environment, run your handler inside it, and bill you for the milliseconds used. The key engineering trick is Firecracker, a tiny virtual machine technology AWS built to boot a secure micro VM in about 125 milliseconds, far faster than a normal VM. You deploy code and config, and Lambda stores the package and records your memory setting, where CPU is allocated in proportion to the memory you choose. An event fires, such as an API gateway HTTP request or an S3 upload notification, and the Lambda service receives it. Lambda checks for a warm environment, a micro VM that already ran your function recently and is sitting idle. On a cold start, Lambda launches a fresh Firecracker micro VM on a worker host, loads the runtime like Node or Python, then loads your code, adding 100 to 800 milliseconds depending on package size. Lambda runs your initialization code once, then calls your handler with the event payload. Your handler returns a response, which travels back through the trigger to the caller. Lambda keeps that micro VM warm for several minutes, so the next event skips the cold start and reuses everything outside the handler. If many events arrive together, Lambda boots many micro VMs in parallel, one per concurrent request, up to your account concurrency limit, which defaults to 1,000 per region. Picture a photo app. A user uploads to an S3 bucket, which fires an event to a Lambda. The first invocation that morning cold starts. AWS boots a Firecracker micro VM, loads the Python runtime and the pillow image library, then resizes the photo, taking maybe 600 milliseconds total. The next 200 uploads in that minute reuse warm environments and finish in 80 milliseconds each. If 500 photos land in 1 second, Lambda spins up 500 micro VMs in parallel, processes them all at once, then lets them go idle and reclaims them minutes later. The bill is the sum of milliseconds across all invocations times the memory size, often a few cents for the whole morning. The biggest misconception is that a cold start happens on every request. It only happens when no warm environment is free, which is the first call, and during sudden scale-up. A second misconception is that one Lambda environment handles many requests at once. Each micro VM serves exactly one request at a time, so 100 simultaneous requests means 100 environments. People also assume more memory only buys RAM, but Lambda ties CPU to memory, so raising memory can make CPU-bound code finish faster and sometimes cost less. Like that pop-up stall that appears only while an order is cooking, Lambda runs your code inside a single request Firecracker micro VM that it creates on demand, keeps warm to skip cold starts, and scales by launching one isolated environment per concurrent request. Every day, I break down one cloud system to its real mechanics. So subscribe to Tech with Joel and learn how the cloud truly works. What is the worst cold start delay you have ever measured? Subscribe to Tech with Joel.